In this video, we'll talk about another set of addition reactions called hydration reactions. And these reactions, what we're doing is exactly what it sounds like we're doing. We're hydrating alkenes, we're adding water across a double bond. So if this is the alkene, right, and X and Y would be an OH and an H. So we added the elements of water, H2O, across a double bond. There's three different ways we can perform this reaction. We'll talk about all three and why you might want to use one way or another. So the first way to hydrate alkenes, which is the easiest and most straightforward, is called acid catalyzed hydration. So we could also call this acid catalyzed hydration. It follows Mark's rule, meaning that the hydrogen went to the less substituted carbon and the OH went to the more substituted carbon. When you see H3O+, there's lots of different ways we can represent this, right? When you add an acid, a strong acid, to water, remember that it disproportionates to hydronium ions. So H3O+ is a shorthand for something along the lines of sulfuric acid. If we take sulfuric acid and we add it to water, this is called dilute sulfuric acid because we have a small amount of sulfuric acid dissolved in water. So these two things are the same, two different ways of saying the same thing. Okay, so let's look at the mechanism of this reaction to try to understand what's going on here. So let's start back at the same alkene that we had on the previous slide. And let's draw out the hydronium ion. We have H3O+. Okay, so just like in hydrohalogenation, in this particular addition reaction, we have the pi bond, which is electrons which are relatively reactive, and we have a partially positively charged hydrogen. We have an acidic molecule. So what's going to happen is we'll protonate the alkene to generate the more stable carbocation and a molecule of water. And so that's the reason, again, why the hydrogen goes to the less substituted carbon, right? Because that generates the more substituted tertiary carbocation. So here's where we're at initially. Just like before with HCl, right, we would protonate this carbon and generate tertiary carbocation. But now our nucleophile will be water instead of a halogen. The only nucleophile that we have present is water. And so this is going to start looking like an SN1 reaction. Now we have a carbocation, we have a nucleophile. You want to be careful to draw the product of this step, right? So remember, water is attacking, so we don't get an OH, we get a protonated version of the alcohol product. This water has a formal positive charge. And so to generate the alcohol that we observe as the product, what we need to do is a proton transfer step with more water. So a lone pair of electrons on a molecule of water will accept one proton to break that OH bond, and the product here that we get is the alcohol, where we've added H2O across this double bond. Notice in this step we consume the hydronium ion, in this step we regenerate it. So the acid is just a catalyst for this reaction. It's neither consumed, it's not consumed as part of the reaction. So we could say, if we wanted to, it's consumed in this step, but it's regenerated in this step. So this is acid catalyzed hydration. I want you to be familiar with this mechanism. Remember, this is proton transfer. This is nucleophilic attack. And this is proton transfer. And remember that the hydrogen goes to the less substituted carbon. This is called Mark's rule. And that's just to generate the tertiary carbocation, which is more stable. Okay, so this reaction is the exact opposite of another reaction that we've learned previously. So in the previous slide, what I just showed was if you take an alkene, such as this one, and you react it with dilute sulfuric acid, which means a large amount of water, what you'll get is a tertiary alcohol. We know that if you take a tertiary alcohol and heat it with concentrated sulfuric acid, what you'll get is an alkene. We call this an E1. This is the only way you can get E1 as a major reaction pathway. This is an addition reaction. So how do we know which side is going to be favored? How do we know which way the reaction is going to go? Well, what we need to do is just understand Le Chatelier's principle. So let's think about this. If we have an alkene plus water and a sulfuric acid catalyst, the catalyst is not being consumed in the reaction. We get an addition of water across the double bond, right? To give this product, right? If we take this and we heat it in the absence of water with sulfuric acid, we go back in this direction, right? Remember in Le Chatelier's principle, if you add a large excess of one of the reactants, that shifts the equilibrium towards the products, right? So we can adjust this equilibrium just based on how much water is present. And if we go back to the previous slide, this might become a little bit more clear. If we have a large excess of water, which is what dilute sulfuric acid means, a small amount of sulfuric acid dissolved in water, we have a large excess of this reactant, which is water, so we're going to shift the equilibrium towards the addition reaction. If we remove water from the reaction, that's going to shift the equilibrium towards these elimination products. So we can shift the equilibrium just depending on how much water that we have present in the reaction. Okay. Remember, anytime you're generating a carbocation in the reaction, then you have you generate a new stereocenter in that reaction, you have the possibility of forming racemic mixtures because in this particular case, the carbocation that would be generated is flat, and we're generating a new stereocenter because we have methyl, ethyl, propyl, and hydroxyl. And our flat carbocation can be attacked from the front or from behind. If it gets attacked from the front, we get this alcohol. If it gets attacked from behind, we get this alcohol. So hydration, acid catalyzed hydration, will produce a racemic mixture if a stereocenter is being formed in the reaction, just like a hydrohalogenation reaction. Okay, so and remember, just like in a hydrohalogenation reaction, if we generate a carbocation intermediate, that carbocation intermediate can rearrange. So let's look at this reaction. If we take this alkene and hydrate it, the first step is protonation at the less substituted carbon. So we get a secondary carbocation, right, that looks like this. That can rearrange to give us a tertiary carbocation if we have a methyl shift. And that tertiary carbocation will go on to form this product, right? And actually the rearrangement product will be the major product. So anytime you have a carbocation intermediate, you'll see rearrangements. And sometimes you won't want the rearrangement product, you will want this product. So in order to avoid rearrangements, what we need to do is avoid carbocation intermediates. In order to avoid carbocation intermediates, another possibility is called oxymercuration, demercuration. In the first step, you take an alkene in the presence of mercury acetate and water, and you get oxymercuration. So you get a mercury atom here. In the second step, you get demercuration, which removes that mercury atom and replaces it with a hydrogen. Notice that we've added water across a double bond, but we haven't seen any rearrangement. And the reason is because there's no carbocation intermediate. Let's look at the intermediate that is generated from this reaction. Okay, so this is going to look a little bit strange, so just bear with me. Mercury acetate is a mercury atom that has two acetate groups. An acetate group just looks like this. And so what can happen is this acetate group can easily leave to generate a mercury plus, which is a good electrophile, right? We have a lone pair of electrons. So you can think about this kind of like a really big, fluffy H plus. Instead of a proton, we have a mercury plus. And just like in the hydration, acid catalyzed hydration, the alkene will attack a proton to generate the more substituted carbocation. It's the same thing here. So this pair of electrons from our double bond attacks the mercury ion. We get something that looks like this. But the difference between mercury and hydrogen is mercury has lots of other electrons. So we don't technically generate a carbocation. At the same time, the better mechanism to draw here is that at the same time that we attack the mercury, this lone pair of electrons attacks what would become this carbocation, which gets us to something that's called a mercurinium ion. It's a three-membered ring that contains a mercury and two carbons, right? So we have a nucleophilic attack followed by another nucleophilic attack to form a three-membered ring that looks like this, right? But one of these bonds is actually much weaker than the other bond. This bond between mercury and this more substituted carbon is going to be weaker. And that's going to be important when we look at the next step. So this is oxymercuration. So the first step in this mechanism is oxymercuration. And the first step in oxymercuration is generation of a three-membered mercurinium ion. Okay, so how will that react under these reaction conditions? Well, what can happen is that I said this bond is weak, and the reason is because we said this mercury is positively charged. It wants to dump some of that positive charge onto the carbon that's next to it, right? This is a tertiary carbon, and this is a secondary carbon. So the tertiary carbon can accept more positive charge. So if we have a mercurinium ion, and let's say we have water as the nucleophile, the water is going to see a buildup of partial positive charge on this carbon and attack that carbon to open up the mercurinium ion. And then after loss of a proton, what we're going to have here is an OH on this carbon and a mercury on this carbon. So after step one here, first thing that happens is we generate that three-membered ring, which then gets opened up by water, and we have a proton transfer. So 3 steps to get OH here and mercury here. And then we add sodium borohydride, which you can think about as an H- ion, which is going to kick off the mercury and replace that with a hydrogen. So notice that what we've done, we've added water across this double bond. We have an OH on the more substituted carbon. We have hydrogen on the less substituted carbon. So oxymercuration, demercuration also follows Mark's rule. But even better, there's no rearrangement. So what I would like you to remember is that acid catalyzed hydration and oxymercuration, demercuration both follow Mark's rule, just that acid catalyzed hydration will undergo rearrangement if that's possible. So the only time that you want to use oxymercuration, demercuration is to avoid carbocation rearrangements because mercury is relatively toxic.